Today, we Group 8 is presenting our project, which is design of a stepper motor control system. A stepper motor is a brushless synchronous electric motor that converts digital pulses into mechanical shaft rotation. It is widely used for its precise positioning, such as in hard disk drives, robotics, antennas, telescopes, etc. To control the action of this motor, we need a specific motor driver. We have followed the mechanism of L298N motor driver and implemented the motor's control mechanism for bipolar stepper motor in MATLAB Simulink. We were able to control the speed, angle of rotation, and direction of the motor with our controller. So basically, our motor driver can take three inputs: speed, angle, and direction. Based on the input provided by the user, appropriate clock pulse is given into the MOSFET gates. When MOSFETs are in on state, it energizes the coil of stepper motor and allow it to operate up to the desired angle. In our Simulink model, we have used scopes and display to verify the input and outputs. There are mainly three driving mechanisms, such as full step, half step, and micro step mechanism. In our project, we have used full step wave drive mechanism for our motor controller. In full step mechanism, we can see that two coils of the stator are energized at the same time. At the first step, the coil A and B is energized, and the second step, we can see that B and A prime is energized. Then, at the third step, we can see that A prime and B prime is energized, and at the end, step 4, we can see again B prime and A is energized. We can see from the graph that A and A prime has a complementary pulses, and which is also true from B and B prime. Here we can see that desired pulses for full wave drive has been generated according to the previously mentioned method in our Simulink model.
In this project, we have followed the design of L298N driver with some minor modifications. L298N is a well-known motor driver for DC motor control. It is a dual edge bridge motor driver which can control speed and direction of two DC motor at a time. This driver can also be used for stepper motor speed, angle, and direction control. In this slide, we can see the working principle of single edge bridge. Using complementary gate signal, we can run the motor bidirectionally. We can also change the speed by increasing the voltage. Here, dual edge bridge is shown, which is similar to our bipolar stepper motor driver. Output of edge bridge, here A prime coil, and output of another edge bridge B prime is connected with the coil of stepper motor. Here we can see the two winding of stepper motor. Now we can see that internal circuit diagram of L298N motor driver, which is collected from the datasheet. Here we can see some extra pins, enabler A, enabler B, and some current sensing pin. Here we use some modifications and simplified our design. We have used our MOSFET instead of BJT in this circuit diagram, and also ignored the current sensing pin and an enabler pin.
For controlling part, we use
These are two
Simulink
gate signal for
workspace.
phase
Here
1
we
of
will
stepper
give the
motor,
input
and another
values
is
for
for
the
phase
angle,
2 of
direction,
stepper
and
motor.
speed. Angle should be given in degree, speed should be given in degree per second, and direction value is 1 for clockwise rotation and -1 for anti-clockwise rotation. With this variable, all the parts inside the Simulink is controlled through some equation. Our generated pulse gives 4-degree rotation over full time. As speed is inversely proportional to the time period, the relation between time period and the speed is shown here. From here, we can get delayed for each pulse generator, which will be 1/4 and 1/2 of this time period. For stopping at the required angle, we need to stop the pulse. For this, we use reflected delayed step and use logic gate with this pulse. The delayed time, also can be called the final time, will be degree required divided by speed. For simulation part, first let's set the input variables. For this, we have to go to modeling, model explorer, go to base workspace. Here we have to create 3 variables. One is deg, another direction and speed. Deg is for the final output angle. Direction is clockwise rotation for 1. Direction is -1 for anti-clockwise rotation. speed is in the degree per second value. Now let's see the equation inside each pulse generator. For the first pulse generator, which has 0 delay, second pulse generator, which has half of the time period delay, which is half of the time period, and third generator is 1/4 of the time period. Delay is equals to 1/4 of this. And the fourth one is generated by subtracting the third one from the unit step. So this is a unit step subtractor, and this pulse is generated. In the MOSFET section, the first pulse from this terminal goes from this to MOSFET. So current will come from this battery, from this terminal. From here it will go through A phase and come out of A prime phase and come through this ground. And for the other pulse, current will enter this MOSFET, then go to A prime phase first and come out of A phase and go toward ground. Now let's see the delayed period. So delayed equation was degree divided by speed, as explained earlier. Here the output is shown in radian, so we have to multiply it by 180 divided by pi to get degree. This one is error minimizer, and this shows the speed angle output, and this one shows speed output. Now let's run this. So our final angle should be 97, direction is clockwise, speed is 10. Let's run this. As we can see, there is 1 degree error because we didn't use the error minimizer. For using the error minimizer, we have to check another thing for the negative angle rotation error. Let's run this again. So here we can see there is another 1 degree error. So error minimizer, inside error minimizer, we can just give 1 and run again. This one is running in anti-clockwise direction, so the value is negative and speed is also negative, and we can see there is no error in the result. Now let's change the value for degree, let's say 177 degree and positive side, means clockwise direction, and run again. So we can see there is no error.
Conclusion. This simulation model can be used in practical stepper motor controlling. Further improvement methods such as current sensing pin can be added to ensure the safety of the driver. For proper functioning, heat sink should be attached with the driver.